Good afternoon, everyone, and thank you for attending our Electric Industrial Process Heaters webinar today. My name is Ed McMahon, sales engineer here at Liberty Electric Products. Before we get started, I want to let you all know that everybody will be muted during the presentation. If you have any questions as we go along, just go ahead and enter them into the questions panel located in the webinar control, and we'll try to get to all of them at the end of the presentation. If we don't have time to go through all your questions, we'll be sure to reply back to you by email. This webinar is being recorded and will be posted both on our slide deck on our website and the YouTube channel. Our presenter today is Rob Zerillo. Rob has been designing engineered heating products for over 26 years. He is currently the heating and ventilation product manager here at Liberty Electric Products, where he focuses on working with engineers and contractors to design and supply electric heating products for many different industrial and commercial applications. While this particular class is not yet an official PDH, we hope to have that done soon. We do have several classes that we do offer that are registered with the state of New York, and Rob can give them on site or virtually, should that be of interest to you. And you can get a list of all of those programs that we offer at no charge just by going to our website. So with that, I'll turn it over to Rob.
Thank you, Ed. Thank you, everybody else, for spending 45 minutes with us this afternoon. And we're going to go through electric industrial process heaters. So as we get into the presentation, just want to cover the agenda real quick. As you can see, we're going to cover a little bit on heating basics because I don't really know what the level is of everybody in attendance. So there's a few things that we just want to make sure that you understand a little bit of the terminology, the jargon that you'll typically see associated with electric heat applications. And then we're going to go through and talk about each of the specific heater groups that you will most prominently see within these types of applications. So component heaters, process air heaters, immersion heaters. We're going to spend a little bit of time on that one because there are several products involved in it. Infrared, radiant and infrared heaters, large capacity systems, hazardous location. We're going to talk about some process heater controls. And again, this is a topic that we could spend more time on than we will be today, but we just want to get you some familiarity with some of the more common controls. And then we're going to talk about tank heating, which is a very popular application where electric heat is in use, and then some heat tracing and offsetting losses, and that should wrap it up for us. So I'm going to try and keep it to 45 minutes, and why don't we go forward? So let's talk about some of the advantages of electric heat. Electric heat, from my days on the boiler side of the business and mechanical rooms, this is a very low complexity installation. The one thing that I really like about electric is that you're literally bringing power to a unit, wiring it. It's pretty much away you go. So, in these changing times as well, it's a green friendly option that does not have any, direct carbon emission to it. These are low noise. At best, you're going to hear some humming to it. Very little to no moving parts, if anything. The only moving parts that might be in conjunction with something like an air heater might be a fan blower with it. The one thing I like as well is that you can test elements for their longevity, and depending on what the resistance readings are coming back, you can actually predict the rate of wear on these elements and proactively change them out before your process is disabled and you're down and losing money. So I think that's a very important feature. The thing that I also like the best is predictable operating costs. If we know what the kWh rate is in a particular area and the size of the heater, it's very easy to determine what your operating costs per hour are going to be. And then, of course, compared with some of your larger heating equipment out there, such as boilers, there could be a substantial physical footprint savings with electric heaters. So some of the design considerations that we typically go into when addressing each application, as they all are different, are heat losses. Heat loss is a big one, and we need to think about that in terms of how do we compensate it and make up for it. We also look at the physical footprint. As we just mentioned, sometimes we're in space-constrained areas, and whether to orient a particular piece of equipment horizontally or vertically can play a role in that. How do we want to control it? There are several control options where, hey, I don't need something fancy for this application versus I want precise temperature control and better longevity out of my elements. And then, of course, what is the heating element going to be subjected to? Is there corrosives or issues with caustics or acids where we have to worry about what type of sheath material we're going to use to for the heater itself to come in direct contact with. Another thing with heating basics is there's three main types of heat, and I think it's important to identify, which is which. And conduction heating, just to go through those three pretty quickly, conduction heating is direct contact transference of heat, okay? And an example that I came up with that seems to make sense to pretty much anyone is, if you look at it, say an electric oven, the flat ceramic cooktop, nice and smooth. So when you put your pot or pan on it, you've got direct surface to surface contact, and you are heating directly surface to surface. Convection heating is utilizing air. It's basically using heat within the airstream to evenly heat whatever that object is that you're trying to achieve. So again, as you can tell, I was probably hungry when I created this application, because now I'm using an air fryer for an example of an appliance that uses convection. So you've got a heat source within that air fryer, and then a fan that swirls the air around to cook the food evenly on every side. So that's an example of convection heating. Radiant infrared, it's kind of one and the same. Okay, you've got heat energy that's emitted from a heat source, which is your radiant heat. But that heat comes out in different wavelengths. And depending on that type of wavelength, that is an infrared wavelength that is directly heating an object and not so much the air around it, okay? Radiant infrared heaters can directly change the air temperature, but it's doing it by heating an object in that space. And once that object becomes warmer than the ambient air around it, it begins to change that air temperature surrounding the object itself. So our best example of a radiant heater is sun. When you walk outside on a cold day and the sun is shining, it doesn't feel so bad when you're in direct sunlight. If a cloud passes over the sun and blocks it and blocks some of those infrared waves from you, it feels almost like it got 10 degrees colder. Well, the air temperature didn't change any. It's just it blocked the waves getting directly to you and warming you. So hopefully that makes sense. Another thing that we have to consider is what type of material are we going to heat? We've got gases, liquids, solids. And gases is about the easiest one. It's simply, if you think of it like air, I mean, you're just basically pushing a gas or an air through a heating element and heating it up. So you can either recirculate that air and gain higher temperature increases off it, or it could be a one shot through the air heater like a duct heater for a given temperature rise. We've got liquids, which is an extremely common application in industrial. And we've got different types of liquids. So there's heat tolerances for water, for different oils, for glycols. So what we're looking at is what kind of viscosity and heat tolerance can that material take. Water is the easiest to heat and can take the highest amount of watt density at 52 watts an inch. And then, of course, we've got solids. And solids are very much weight dependent as well, like a liquid. The weight and the thermal conductivity of the material itself play a role in how quickly we can transfer heat to that particular material. So if we think of things almost like I've got a 10-pound brick of copper and I've got a 10-pound brick of wood. Copper is very heat conductive. It transfers heat extremely well. So in that case, versus something like wood that is dense and does not transfer heat very well, we've got different warm-up times and may require different amounts of heat to affect it. So why don't we dive into some of the heaters themselves? And component heaters is a good place to start, because it's such a unique and there's a wide variety of different types of component heaters that are used in industrial manufacturing process all day, every day. And it can be something as simple as a strip heater to cartridge heaters, flexible heaters that are made from silicone laminate or Kapton. And they're all unique to their own applications. So depending on what type of heat is required, I've got a couple of pictures here on the right, and one of them is a plastic extruder that you can see on the top. I mean, these heaters can be used either singly or chained together as multiple heaters acting as one. Typically on something like an injection molder, piece of equipment such as that, we'll have several band heaters that may surround the barrel, the discharge barrel of that former, so that you can cover a wider area of tubing with heat. So you can chain all those heaters together and let them behave and act as one. And then you've got something like a ring heater that can be used in a yogurt plant, where when you want to stamp down the foil lid on a yogurt cup, you've got a singular circular heater like in the bottom right-hand picture on that graphic there of just a heater that's heating up a small piece of metal, a metal disc, and as that machine comes down, it's applying, say, the stamping process to a piece of plastic, and away you go. So these heaters are very predictable. They do come in a multiple of different terminations, lengths, sizes, diameters. So really, it just kind of comes down to what's your application and what kind of component heater do you need for it. Here's a few pictures that I pulled that are pretty indicative of how component heaters are typically used. The upper left-hand picture is a heated plenum. And I like that picture in particular because you see all the leads coming off for some of those heaters. Well, the silver stubs that are in between each of those leads are heaters, cartridge heaters coming back in the other direction. So here's an application where they put a lot of heat into this plenum. It's usually used in something like rubber or plastics forming, where you've got a hot metal press that's coming down and forming a piece of material or fusing it. But this is an example where it may have a high heat requirement, where there's that many heaters, so they want a really fast warm-up time for their system. The middle picture with the glowing orange rods there, those are just simple tubular cal rod elements. I mean, those are found everywhere in industrial applications, can be used even in radiant applications as well. The cutaway is a nice picture that shows you a bit of the anatomy of what's inside of one of these tubular heaters, and they're actually quite simple. So, you've got a couple of helix coils with a resistance wire in there, and magnesium oxide as the insulator, and then whatever your outer sheath material is. What I do think is pretty interesting factoid is many times those resistance wires are as thin as 37 gauge, which is, to put that in perspective, that's about a third of the size or diameter of dental floss. So it's really thin stuff, and you can hit it with 480 volt, even 600 volt, and it holds up for years. So I've always been pretty impressed by that. Bottom left-hand corner, if you open up a electric range oven, when the next time you walk through a Lowe's, Home Depot, or an appliance store, that's a great example of showing a multiple bend tubular heater on the bottom of an electric oven. So we'll see these things in all kinds of different shapes, configurations, and outputs. And then in the bottom center picture is a Kapton heater. This is a flexible, very small, very powerful kind of heater that is usually used in specialty OEM applications. If anything, silicone laminates are another example of a flexible heater where I once visited a dessert factory. They literally made cakes, pies, all kinds of things for the restaurant industry, and they used thick-on silicone laminate heaters on the back of a machine that drizzled chocolate, which was trouble for me anyways. But at any rate, it gave them a very easy solution to where they could peel the heater off at the end of a shift, clean the material, reapply it during the next shift. And I thought the interesting part about it too is because those heaters do not operate to very high temperatures, you can't, they had it set to where you couldn't burn the product, which is ultimately what the goal in manufacturing is, right? Produce it quickly, produce it accurately. And then of course in the bottom right-hand picture, this is just a nice example that depicts you don't want to have an air gap whenever you're inserting a heater into a space. So if we consider our plenum in the upper left, if we have air gaps where those are, which I like the design where they came out with the heater on the other tip to know that it made it all the way through with no air gap. Air gaps are dead space, and it's like an insulator that will cause that part of the heater to wind up developing a hot spot and eventually burn out. So we want to make sure when we're using things like component heaters or specifically a cartridge heater that we have direct contact or conduction contact as we're using them and applying them. Process air heaters, very common as well in industrial facilities, typically used for like curing and drying and annealing processes. A lot of times you'll see something come down a conveyor line. It has to go through a particular chemical dip or some sort of anodizing on it. As it continues down, they want to dry that off and get it to cure quickly. So process air heaters are really good for that application. And again, it's a product that can be engineered specifically to a particular output, size, voltage requirements. And these heaters are, again, powerful. They can get up to 1200 F. I mean, essentially inside of this heater, you really just have the guts of tubular heaters on the inside of it. So again, it's the same laws of physics apply to those component heaters we just looked at. So there's also, various sheath materials that can be used and tons of different terminations. And these heaters can also be designed for specifically for explosion resistant applications as well. So class 1, div 1, class 1, div 2 applications with spark quenching power connection boxes on them are available. Process heaters typically come in either a fin tube or a nichrome element. And to just give you a quick difference between the two of them, a fin tube element is something like you might see in a baseboard heater, okay? The fins on them is that you'll have a tubular element with a bunch of aluminum fins or copper fins or whatever that material is, steel. If it's got to be anti-corrosive, it's stainless steel, but what it does is helps the transference of heat. So as that element is warming up, it's transferring heat to those fins, which is also helping to take up more surface area within that heater and pass more air through it. These are usually very robust. They handle moisture a lot better than the open coil version does. An open coil heater looks like the inside of your toaster oven. If you've ever stuck your head down or looked down into your toaster oven while it's running, you see those orange hot, they almost look like wires cutting across there. Open coil elements are basically nichrome cables, I guess, or wires for lack of a better term, that are usually connected with ceramic discs because the ceramic can take the heat. They're usually less expensive to produce, and they are very effective. They actually last a very long time as well, but they don't do well in high humidity or moisture applications where you get some arcing going on inside of there if it takes a little bit too much humid air. The one thing that I would definitely stress with air heaters as well is you'll always want to put like an air proving switch in line with your process. And what an air proving switch does is it just looks for positive air pressure so that you couldn't have a situation where the heater is running and there is no air passing across the element, because that will burn it out. Just like we talked about with that cartridge heater, that buildup of heat has no place to go. So we either have to put it against a solid and transfer that heat, or we push air across it to cool the elements. So very important to use air proving switches. And here's a couple of examples of process air heaters and in industrial facilities. They are very common in batch ovens, usually the smaller ones. It's an application dependent type of selection as well. I mean, if we were to look at something like, Corning glass, I mean, that's an application where, yes, a gas-fired furnace is going to serve you a lot better when you're trying to heat up extremely large volumes of product. Electric air heaters, however, can also be extremely precise in their temperature control, which is a big attraction to these as well, is that they're excellent at maintaining within 1 degree set points versus gas units. So it's really more of an application-driven thing. Immersion heaters. Immersion heaters are really common, and probably the most noticeable one that we see a lot is screw plug immersion heaters. These are the smallest in your immersion heater family, and these are connected to whatever appliance or device they're going into with a threaded NPT connection. So they just literally screw right in, and you wire them up and away you go. So a common application for these are something like an electric water heater. You could go find one of those in almost any hardware store, and when you remove the element, you'll notice it's a screw plug immersion heater. So these can come in several different sheath materials as well. They actually go all the way up to about 18 kW, which is pretty significant heat load. I think that equates to around probably 52 or so, 52,000 BTUs. Excuse me. So you can get quite a bit of heat out of these. They can be configured to different diameters, typically nothing past 2.5 for an OD, and they can handle input voltages of 120 to 480. So lastly, the terminations can be made moisture resistant, so they'll use a silicone caulking almost on the inside of the unit to prevent any sort of water ingress. And that termination enclosure, you can have explosion resistant, where again you're using a non-ferrous material or something that's spark proof, and then of course just your general purpose elements. So an over-the-side immersion heater is exactly what it is. It's I think we found a couple of pretty good graphics to put in with this slide as well. We don't see quite as many of these as we used to when we had a much more robust industrial segment. This is a product that is used pretty much specifically for open top tanks. And they're popular in plating operations, or places where, again, you've got chemical dip tanks. Again, this is a very versatile heater where you can alter the height of the riser itself, or the vertical dimension of that heater. So again, if you've got a tank that's 6 foot high or 4 foot high, we can change that riser to ensure that your termination box is obviously outside of the heater, and that the heater itself is down near the bottom of the tank and doing what it's supposed to do. So these also have a wider range of element materials because of what they're subjected to. We can get into fluoropolymers and titaniums and quartz. I mean, so there's some pretty exotic materials that can be used for these, but almost all of it has to do with corrosion resistance. Again, same thing as far as the kW ranges go, and whether or not you'd want the termination to be a general purpose, moisture resistant, or an explosion resistant. Flanged immersion heaters are probably the most common, and it's really because the sizing of this can go from, anything from 1.5 inches all the way up to as big as you want it. These heaters are very much the do-all of the fluid heating world, you could say. It's a heater that, again, you can use a variety of different sheath elements or materials for anti-corrosion resistance. One of the things that I am impressed with is that you can go all the way up to 2000 kW. I mean, that's a big, big number. I mean, 2 megawatts on an immersion heater is, I still have yet to see one that big, but, again, no matter what the size is, they can be made. It's a lot of them will just go to a made to order type of status. So again, same thing with your voltages and with your terminations as far as moisture resistance, explosion resistance, etc. And that brings us into circulation heaters. I mean, this is really just an extension of a flanged immersion heater. The circulation heater is that because we provide a vessel with an inlet and outlet to pair with that flanged immersion heater. So this is really more like a packaged unit, and these can be constructed with controls on them, everything from simple bulb and capillary thermostats. We can put overtemp thermocouples or RTDs on these, which are always a great idea. And again, that's going to serve much like the air proving switch that we just discussed with process air heaters, in that, an overtemp thermocouple can really prevent some damage, and save what could be an expensive heater. If that temperature ever reaches a certain point, it'll cut the heater out. So we do highly recommend high limits with them. And to control these, we can use pretty much any means. I mean, the most common are your contactor relay panels and SCR controls. I really like the SCR controls with these because when we regulate the voltage or current going to the heater, we can very much, precisely dial in that heat to literally within tenths of a degree. So your control with an SCR is excellent. And it also soft starts the heater to help add more longevity to it. So radiant and infrared heating. It's another interesting application where there's a lot of different uses for it. And typically in the industrial segment, I've seen this more with plastics forming, rubber again, or in applications where it's either cooking or someplace where you would not want any dust to get in there. Because a radiant heater is heating an object in front of it, it doesn't stir the air up and promote dust or any sort of impurities from getting into the material that you're producing. So again, we're taking an extreme heat source and it's radiating that heat outwards towards the object itself. Now, there's different types of wavelengths that we deal with infrared radiant heating, and we've got shortwave, medium wave, and long wave infrareds, and there is, certainly layers of separation in the in-between, but the gist of it is that shortwave heat is typically very intense. It doesn't travel nearly as far as the other two wavelengths do, but it is an intense and harsh type of a heat. So you can typically do more, you can heat more with less when you're talking about a shortwave infrared. And they're also probably it's the heater of choice that you'd want to use if there's ever a threat of cold air intrusion into the space, or if there was forever reason to do outdoor heating. That's your best bet with it. Long wave infrared travels the longest distance. It's the most comfortable on human skin, but you're typically not going to find long wave infrared unless it's something that is just very, very specific to a material or a process to create a material. but typically long wave infrared and medium wave are meant more for human comfort versus industrial process. So if anything, when we look at this, the big advantages are that, again, you're not stirring any air with it. They are popular in things like curing boots. Personally, I think that they work well for paint curing. It's if you can get the power connection brought back to the quench-proof or spark-proof box, if you're doing it for, say, automotive, where you've got flammables involved. To the best of my knowledge, there is not a manufacturer yet that actually makes a Class 1 Div 1 rated radiant heater. So they are a bit rare. And again, the heating effectiveness of this is, again, going to be determined, by what wavelength you're using, how much wattage, and the distance from your heater to the object that you're trying to heat. One other factor too that is important to mention about these is what is the absorption level of the object you are trying to heat, because some objects will reflect a portion of that infrared wave, and some of them will just soak it all up. So obviously our heat transference is better with objects that absorb it, and we have to compensate when we're talking about reflective objects. Okay, large capacity electric heating systems. Again, kind of says what it is. It's these are just ways that the electric industry has kind of overcome standard boilers, let's say, or even furnaces or fluid transfer we can do with electric now. So there's a lot of different applications that this can cover, and these are typically all products that are on a made-to-order type of basis. Some of the big advantages to this, again, are that they don't create noise aside from the humming, and there's no fuel piping in or emissions out of the unit itself. When you've got predictable wear factors, like, again, testing your elements for resistance and being able to pretty much predict your preventive maintenance schedules on these, it certainly creates an application for a lot less downtime versus mechanical systems that could pretty much break at any given time. When we look at it as far as your ratings are concerned, I mean, that's got about as many ratings at this point as a TripAdvisor page, and I think that a lot of those have really come about because of innovative requests to use electric heat in different applications, and obviously to have a corresponding rating to ensure that it's safe and accepted, for that. But again, we can take fluid and oil temperatures up to around 750. I was always impressed, having come from the steam world, that PSI up to 450 F isn't really that big of a deal, because that's the pressure rating of your vessel. But an output of 22,000 pounds per hour, if my math is still okay, it's been about 11, 12 years since I've used that steam calc, but I think that comes out to about 500 horsepower in boiler size, which is pretty good size boiler. Air temps up to 1200. Again, Colorado Element, that's what they put out. Okay, so hazardous location heaters. We did touch on this a little bit with air heaters. The big gist of a hazardous location heater is the ability to quench spark at the point where we bring power to the unit. Okay, these heaters are designed with non-ferrous materials, so that we're not promoting anything that can create a spark, because hazardous location heaters are typically used in areas where you've got combustibles. So it's not that common, in the case of, say, something like rubber or plastics forming. But if you get out onto a gas compressor site, that's a whole different story, and everything is going to be hazardous location rated. So again, this is just versatility of the equipment itself, in that it can be done, and it can be done safely. So hazardous location controls, going hand in hand with the heater itself, we have single circuit, we have dual circuit type, controls that can operate hazardous location heaters. Oftentimes we found that the best remedy, if you can avoid it, is to actually bring the controls outside of the classified area. So if we've minimized, and derated the classification, we can oftentimes have a larger variety of controls to use with that application versus being confined to just what is available in a Class 1 Div 2, Class 1 Div 1 housing and termination. Okay, process heater controls. Process heater control is interesting. You know, this is a topic that I think we could spend quite a bit of time on. So I'm going to keep it short and just go through some of the real basics of this. And the first slide here with the interlock controls, I think is a must in a lot of these industrial process applications, especially with your air heaters, your circulation heaters. You know, I would say pretty much anything that you spent some considerable money on, you want to protect it. Interlock controls are a great idea. So limit switches, you know, these get wired right to the contactors or the controls of the heater themselves that are either looking for positive air or flow coming across that, you know, heater to ensure that you're always taking heat away from the elements themselves. And as soon as that flow stops, these send a signal to the contactor to shut the heater off. So they help preserve the life of the heater. Level control interlocks are again, very self-explanatory. You'll see these in tank heating applications where we're worried that the level in the tank gets too low and it could expose the element and prematurely burn it up. So we put a level lock control at some distance in between, you know, the low point fluid level and the top of that heater to ensure that they stay covered. High limit interlocks are also a really good suggestion. These are temperature controllers that are hunting for a number. They're just hunting for a temperature. So if you have a process application, you want heat at 300 degrees, but you could either damage the material that you're manufacturing or damage the heater or any surrounding equipment at say 350 degrees, you could set a high limit interlock control at 350. So if that temperature is ever achieved in the process, it's going to cut the signal, cut the power to the heater itself and preserve everything. Single point controls, very common. You know, these are, you know, typically with smaller tank heaters, things like that. You know, they can be everything as simple as a bimechanical or a bimetal mechanical bulb and capillary type of switch, like you see that red box there with the bulb and capillary with it, to a more advanced microprocessor style control, like that small 2-circuit panel you see there in the upper right. So these typically will utilize line voltage 120 to 480 in most cases. Mechanical stats I'm not a huge fan of. I mean, yes, they're inexpensive, but they do have a plus minus rating of roughly about 5 degrees. And by that, I don't mean they're going to be high by 5 degrees or low by 5 degrees. It's more like a 2 to 3 degree up or down, just to clarify that. Process temperature controllers and high limits. I would think most of you folks have probably seen something like this on the DIN rail of a panel, where you've got a simple, you know, PID style controller that can be quickly integrated into a custom panel to operate a particular industrial heater. You put in a temperature set point, and pretty much away this thing goes. You can also use these things with high limits, which is always a recommended idea. And you can get them in heat cool modes. I mean, a lot of the industry has moved towards HMI displays, you know, using more of an integrated automation interface with them, and temperature controllers have dropped in popularity because, you know, again, there's just more advancements in technology and what you can do through a PLC interface versus, you know, the customizations you can do with something like a DIN rail mounted process controller. But again, these are inexpensive, they're very effective, they wear like iron, and they're accurate. Contactor relay panels, again, pretty self-explanatory product. You know, we've got a heater that requires higher amperage loads, you know, something that may require a 100 amp load. A great way to control these things is just through a contactor relay panel, where again, you can mount a temperature controller in there with a high limit controller working in conjunction, and you've got a probe out there in your process that's simply sending a signal back to your panel saying, look, I need to come on at 200 degrees or whatever that number is. As soon as the thermocouple or RTD comes back with that signal, the contactors close, allow power to pass to your heater, and you're heating up your process. So these are very straightforward controls that you know, really are quite easy to design. They're affordable and very effective. This is my favorite one, the SCR panel. I really like solid state relay based controls. These are controls that basically, I guess the easiest way to describe these, that they turn the heater on and off so quickly. You know, you're basically playing with the sine wave, the energy, you know, wave of electric to affect the current going to the heater itself. So In layman's terms, it's almost like having a dimmer, like a light dimmer in your dining room or something like that, where, again, you can either make it bright and full power, or you can kind of twist it down to just dim and barely on. An SCR controller has that type of range to it. And what I like about this feature is that on startup, you're typically soft starting these heaters so that you're not getting that massive inrush current of, say, 480 volt or 600 volt onto directly onto a contactor, and it's being turned on and off like a light switch every 10-15 minutes. I think, as we know, over time, and it wouldn't take very long to where you could burn out those contactors just from the amount of voltage going through them. And something like an SCR helps to soft start that process, which means longevity for your heating elements. By just pulsing that power on at a lower rate and bringing it up to temp, I mean, we can literally double, if not triple, the life of the element just by reducing that initial shock when they come on. SCRs typically turn on off. Zero cross SCRs are 30 milliseconds, and then phase angles are 5 milliseconds. So that's an incredible rate of being able to adjust these. And I think that another characteristic or advantage of an SCR controller is that when you reduce the amount of voltage or power going to the heater and therefore reduce its output, for instance, if I had a 100 kW immersion heater and I wanted to run it at 20%, now I'm only consuming 20 kW and I'm only paying for 20 kW, not 100 kW, which is a little bit different sometimes from gas. I mean, gas, we have to have a certain pressure, and once that pressure is achieved, it's just keeping the pipeline full. But again, this is a precision-based control where you can really hold very close tolerances, to temperature. So between that and adding longevity to your heaters, just a great product to consider for your applications. All right, tank heating. This is probably the most popular of our industrial applications. And for anybody who needs it, please just type it into the comments, and we can get you, these formulas or something for helping you to do tank heating calculations. But there's two different types that we do, and it's either process heating or it's going to be a freeze protection application. What we do typically is take the dimensions of the tank to start off with, and we do a heat loss calculation, because obviously the bigger that tank is, the more heat the skin of it's going to emit. So we have to compensate for that before we can start really changing the temperature of anything that's inside of it. But in changing that temperature, there's a couple ways that we can look at it. There's either, I need that fluid to come up to temperature at a very fast rate. If I need 5,000 gallons heated up in 1 hour's time, it's going to be a much larger heater involved for that type of challenge versus, once I've got the tank up to 100 degrees, I just need to maintain it at 100 degrees, where we can get away with using a much smaller heater that, hey, it may take 2 or 3 days to heat that load up entirely. But once you've achieved it, based on your flow rate coming out of the tank, a smaller heater can often keep up with that process application. When we do freeze protection, typically we're just basing our calculation from 40F down to minus 20F. So we use a 60-degree delta T in our figures, but it's actually a very simple calculation. You're really just taking gallons of fluid, times 8.35, let's say, for water. That's the weight of a gallon of water times whatever your delta T is, and then we divide it by 3412, and that's what gives you the kilowatt needed per hour to heat that load. I'm saying this because if you want to increase that time, everything's based on a 1 hour heat up time in our world here with electric. So if you need it in 15 minutes, I have to actually not only double but triple the size of that kW output to get it down to 15 minutes. Okay, so again, if I use a 100 kW application and I want it done in a half hour, it's going to take me 200 kW to do that. Okay, if I want it done in 15 minutes, it's going to be 400 kW, and so on and so forth. If I want it at 7 minutes, it's 800 kW. So you can just kind of do the math in your head going the other way as well, is that if you're willing to give the process a little bit of time, we can get away with a smaller heater. This is a really interesting product as well that's often overlooked, is electric heaters can be used as a sheathed immersion. Okay, and by that I mean you have a fixed protective sheath that is flange mounted to the tank itself. So if you imagine your tank with a flange coming off it, you can pop in another flange that has a dry well sheath that will insert into the tank itself, and then we can insert a heating element into it that will heat through conductive property with direct contact with that metal sheath into the water or fluid or whatever you're trying to heat up. The cool thing about this is that you don't have to drain the tank to change the heater, which can become a big mess, especially if you're trying to run process or you can't afford to be down, for more than a few hours or that sort of thing. A lot goes into having to bring another tank or some sort of portable reservoir on site to make that happen. So this can become a very, very convenient cost of ownership type of product where you can very easily insert heaters into that protective sheath and rewire them within a half hour and be up and running versus taking literally a couple days to drain a tank, change the heater, refill it, and go through that process. Okay, with tank heating, we often hear open and closed loop systems as well. So I just wanted to make sure, again, based on maybe the experience level of who we got on the call right now, that we just talk about this a little bit. It's pretty straightforward, okay? Open loop systems really just mean that whatever fluid you're pushing through that system is not coming back to be reheated, okay? It's gonna have a single shot duration over that heating element. So if I'm coming out of a tank and crossing over a heater and then going to my process, I've got one shot based on that flow rate to add as much heat or whatever that desired heat level is to your fluid, and it goes on from there. Okay, with a closed loop system, it is recirculatory, which means that water or glycol or whatever it is, or oil that you're heating is coming back through the system and can be reheated again and again and again. Okay, so generally closed loop systems are way more effective at reducing the size of the heater needed, because again, we can recirculate fluid and keep adding to it each time, versus an open loop system where if you have to do a 30 to 50 degree temperature rise on some water going through it, you're going to need a big heater or a very slow flow rate to achieve that type of temperature rise in a very short amount of time. So here's another example of a closed loop system. Hopefully this graphic, for anybody that is, a little bit less familiar with these systems, this should help put it into perspective for you. Is, again, you're coming out of, say, a domestic hot water tank, and your water's nice and warm, and then you're going and heating until that water starts to cool off again, comes back into the tank. So again, no matter where you want to put that heater in the process, I mean, here, the hot water heater is the heater, right? So as you're returning cold water, it heats it back up and sends it around again. So, again, a nice advantage to these is we can right size the heater for the application if we have all the correct information to start, okay? And they are generally lower cost. They're easier to install, et cetera. Open loop systems, again, as we just discussed, generally require a lot more heat to achieve the desired results. So it is not uncommon to see, hundreds of kWs involved with open loop systems. Typically they're not as popular as a closed loop system, but they do come up. The one thing I'll warn you on is that a lot of times I've seen this application dealing with, say, groundwater or freshwater supply, city water, that sort of thing, where you've got a hardness factor, a water quality factor to this. And when you have water that has not been filtered, the solids inside of it will eventually scale onto the elements, reduce the efficiency of that element very significantly. Actually, I think if I recall again correctly from my boiler days, like an 1/8 inch of scale on a boiler was at the time, I think, a 10% efficiency decrease. So it's pretty significant. It's just something you really have to watch when heating raw waters and things like that, is the amount of solids that are in the water, and make sure that your elements stay clean. Ooh. Okay, so we're going to talk a little bit about heat tracing and offsetting the losses, because that goes hand in hand with tank heating. So insulation is your best friend for these types of applications, and quite frankly, it is an absolute requirement for your losses in most cases, okay? So a lot of different types of insulation out there. A lot of it just comes down to, hey, what's the best for the application itself? But when we're looking at a product for offsetting losses on a tank or a pipe, heat cable often becomes a very good solution for this, because it's a flexible heating element. And again, we can wrap it and bend it. And self-regulating cable itself can actually touch against itself without damaging or burning through the cable. So this is a very popular choice that's often used for heat tracing piping systems. And again, what we typically will do is a heat calculation loss to find out how much we have to offset, and then recommend the right wattage cable for that task. Keep in mind that heat cables generally cannot offer up enough heat to actually transfer heat through the pipe itself and affect anything within it. Okay, so it's oftentimes a misconception with it is that we're adding heat or can add heat to the process with a heat cable. When you're talking about Schedule 40 or Schedule 80 pipe, it's not going to happen. Okay, especially now once you put a flow rate behind it, you just don't have enough latency time, that fluid sitting in the pipe generally to affect its temperature change. So again, it's really just a means to offset losses off the system. So when we talk about self-regulating cable, it gets its name because this cable is able to expand and contract based off the surface temperature of what it's up against. And that's how it throttles its heat output up. So there's a standard within the industry, and when we designate a heat cable as, say, a 3.5 10 watt a foot cable, that's what that cable's emitting at 50 degrees F. And the colder it gets, the higher that wattage value increase is going to be. And the warmer it gets, it really doesn't cut back much below what the rated duty is, and that's just due to the construction of how these cables are made. But it is important to note is that, in cases where you're using something like PVC piping because it's maybe just wastewater, you've got to be careful not to put too much heat on that PVC. Now, granted, the cable itself, like a low temp self-reg cable, will only work to a maximum of about 150 F. Oftentimes, if we double this up a little bit too much, it can be too much heat for the pipe. And over time, it can disfigure it. And we just don't want that type of thing to happen. So, let's dial it in with the correct information up front. And, and if it requires special application where we have to use a more robust cable, there's MI cables and constant watt cables that can take higher temperature exposure better than some self-regulating cables can. So another couple of just tips here that we've got in for heat cable is, there's another misconception of, hey, I got to spiral wrap my pipes. Well, not really, okay? Linear runs is probably 95 to 99% of the application where we're just taking one straight shot down the pipe and taping it and then insulating over the top of it, okay? Spiral runs really only work well for fully pressurized systems. As you can imagine, if you're in a non-pressurized system, gravity takes over for whatever fluid is in the pipe and it's going to draw it down to the lowest point. So typically we recommend running that heat cable at, say, 5 or 7 o'clock if we imagine the clock face. We want it on the bottom of the pipe so that as the heat is dissipating onto the pipe, we know it's affecting the part where we're worried most about it freezing or congealing. Okay, so going back to that, I mean, when you look at a spiral run, it's back to our high school math. 3.14 times your diameter is how much cable you're going to use or how much length you need to get around that pipe once. And when you're spiral wrapping, you're going to use about 3 times as much cable as you would to just linear wrap a cable or wrap a pipe, and will often be much more effective. We really only look at more than one run across a pipe when you start looking at diameters that are 4 inches or above. And typically whenever we're using sensing controls, we want to make sure that sensing probe or RTD is kind of opposite position of the heat cable itself, because we don't want false reads. So biggest thing on this for your electricians is, as it says at the bottom, megger. It's a great way to ensure that your install is going to be successful by just testing that cable and ensuring that there are no ground fault interruptions, because these cables, unlike actually a process heater, you don't have to put a process heater on a GFI rated circuit. I think that some facilities do it as a safety rating or safety reason, and that's a good thing. But heat cables do require you to be on a GFI circuit. So we want to make sure that no voltage is leaking to ground when we install these systems and cause nuisance trips. So again, that's what the Megger is going to help you prevent right there. All right, so in summary, because we're getting down to it, really electric heat, at least in my experience from coming over from mechanical world 11 years ago, it's a really versatile product, and there's a lot of things you can do with electric, and hands down, the install is always going to be simpler than a mechanical system. It just is. I mean, you're bringing a power feed to it and follow the wiring diagram to successfully connect, okay? Solid state relay controls, which I told you before, I'm a big fan of because, again, it gives you very precise temperature management, and it also helps, you know, the longevity of your investment. If you're going to, again, invest or spend, you know, $20,000 on a process, you know, circulation heater, you'd like to have this thing around in 20 years. So, you know, again, the SCR kind of more than pays for itself, I think, in the long run. Typically, electric is also going to take up a, you know, less of footprint, and again, you don't have the emissions issues, you don't have flammability or combustion issues, and you know, now I think we are stepping into an era where, you know, you're seeing more renewable energy sources popping up, and plants, facilities are integrating solar, you know, solar generation a lot more frequently than they had in the past. I know out at the Tesla plant out in Sparks, Nevada, they literally generate all of the power they need for that plant using panels along the roof of it. So I think it's something that we're going to see a lot more of coming in the future, and this is a great way to offset, you know, some of those higher, you know, kW requirements, because ultimately that's probably the biggest disadvantage, if I was to mention, with electric heat applications, that we're oftentimes limited by how much power is available in the building. So, you know, it can be very expensive to do full service upgrades with your local utilities. And, you know, again, something like a renewable system, if you can get tax credits, you can get, you know, offsetting credits to help integrate those systems. I mean, now you've got your power generation and your heating equipment all on site, which I think is a huge advantage for a lot of these facilities. And one thing I'll add with that as well is that, you know, utility companies really just have to get the power to your building. They don't have to guarantee what quality that power is coming in. So, you know, integrating in surge controls, integrating in power quality, power conditioning equipment, again, protects your investment for the long run. And it's going to also ensure that your process runs a whole lot smoother, that, you know, you're much more consistent in your power delivery to your equipment. And again, I think it's product that works in conjunction with these process heaters that pays big dividends in the long run. You know, as many of the controls are microprocessor based these days as well, I would strongly recommend having surge protection in front of those control panels. You know, some of these panels can easily get upwards of $40,000, $50,000 depending on the size of that SCR controller. In which case, again, you want to make sure that these are being protected appropriately. So, you know, with that, I think that that pretty much wraps up my time. And I want to say thank you very much again to all of you for spending your time with us today. I hope that, you know, if you've got some questions and you were able to get them typed in, you know, we'll get them responded back to you in you know, quick and orderly type of fashion. And again, if you have any other questions regarding these applications, we're always happy to help. Just give us a call, and hopefully talk to you soon. Thank you.